All right, this is Mr. McCord's chemistry class. We are looking at gas stoichiometry. That's right, stoichiometry is back. Woo! It's never going away, and it's very useful in chemistry. So we're going to calm down a little bit and work through some problems. So stoichiometry is not really going to change much just because we apply it to a different phase of matter. The only thing that's going to be new is we're going to add on something we can do with this to make it a little bit easier. We can skip the ideal gas law to figure out the volume of a gas using that little trick we had before. 1 mole of gas fills up 22.4 liters of volume at STP, standard temperature and pressure, which means we can throw that in as one of our fraction bars to solve for volume. We can also get out of volume if we start with the volume of a gas and turn it straight into moles, which we can then turn into whatever we want, particles, grams, or liters of a different gas in a reaction. So we're going to look through a couple reactions. The first one is something you might encounter if you're not careful with your cleaning products. Whenever you are using bleach, please be careful. Do not mix bleach with other chemicals. Do not get them at the same place. It could be vinegar. It could be, in this case, we're going to use ammonia. It could be toilet bowl cleaner, whatever. Keep bleach away from other stuff because there's a lot of nasty reactions that can release gases that you do not want to breathe in. They are very dangerous. So in this example, we've got ammonia, which is NH3 right here, reacting with NaOCl. This is the active component of bleach, sodium hypochlorite, right? And what we make is NH2Cl. This is chloramine, which is really bad. It's what you usually smell as the typical kind of chlorine smell in pools. So when you have your kind of chlorine disinfectant in a pool, it reacts with ammonia that's floating around from people, like from urine, because that happens. It's kind of gross. And that's where you get the smell from, okay? Same chemical, except if this comes from mixing cleaners in a house where there's not a lot of ventilation and it could be a greater concentration all at once, this can be very dangerous. Okay? The other product we get is sodium hydroxide. Sodium hydroxide is a chemical we'll talk about with acids and bases. It is a base. It's kind of the other thing besides acids that changes pH. All right? And it's also known as lye, L-Y-E, in cleaning products. Also can be very nasty, sometimes used in drain cleaners. It can be harmful to you, to your skin and stuff. So let's say that we're not careful and we accidentally knock over a container of our ammonia, spills into some bleach we've been using to clean the floor or something like that. Okay, so this reaction happens. All right, the amount of NH3 that reacts, we're going to say, is 26 grams, which is quite a bit. This probably isn't going to turn out super well for us. But what we want to find at the other end of this is what volume of NH2Cl gas we're going to make at standard temperature and pressure. Okay, so let's mark some things down. Our goal is to find our volume in liters, specifically for this NH2Cl. Okay? We said STP, so let's make note of that so we don't forget. Let's put it up here. So at a pressure of about 1 atmosphere, a temperature of about 273.15 Kelvin. Hopefully you weren't cleaning at home when it's 0 degrees Celsius. That would be really awful. But just to make the problem work, that's what we're going to assume here. Okay, so in any stoichiometry problem, we want to get rid of the units we don't want to get to the units we do want. Right? If you're using the stoichiometry island diagram, we just need to pop from kind of island to island, bubble to bubble, and see what units we need to get rid of and then how to convert them correctly. Okay? So if we're starting with grams of NH3, that's the first thing we need to get rid of. So I want to get rid of grams on bottom. Specifically, this is going to be grams of NH3, so I should probably actually make some room for that. Okay? On the chart, my next step is moles. Moles is kind of the universal translator between things with different chemicals. If we can get to moles of one chemical that are in a chemical reaction, we can figure stuff out about all the other chemicals in that reaction. Okay? So, moles is my next step. It's the next unit I want to get to. And we're still talking about NH3. Alright, so if all goes well, my grams of NH3 should cancel on top and bottom. Okay, and I should have a new unit of moles to work with. Okay, now in this fraction bar, I've got moles and grams together. Okay, so the relationship in this conversion factor is the molar mass. How many grams of NH3 are in a mole of NH3? Right? So we're going to be 1 with moles. And our molar mass, adding up the mass of 1 N and 3 H's, is going to go down here. Okay, well, on the periodic table, nitrogen is 14.01 grams per mole, and each hydrogen is 1.01. So 14.01 plus 1.01 3 times should be about 17.04-ish, if I'm doing my mental math right. So we have 17.04 grams of NH3 per mole of NH3. Okay? Now, of course, we could stop here, but this isn't the unit that we want. All right? I want to figure out liters of this chloramine stuff I can make, the NH2Cl. So, why bother waiting? I'm just going to keep pushing on. Okay? So, the next thing I've got to get rid of is my molar mass here. Or, sorry, my number of moles. My moles of NH3 is what I got to get rid of next. So, that's going to be bottom on the next fraction bar. Okay, now, my next stop on the stoichiometry diagram is to go to moles of the other chemical. All right, I want to find out something about this chloramine here. Okay, so I can go from moles of one chemical to moles of another. All right, that's the magic of stoichiometry. I can relate things that are in a chemical reaction to figure out something that I don't have measurements on. Okay, now this moles over moles is the only time we can't just assume 1 with moles. We have to look at the chemical reaction equation. Now, thankfully, we actually got a little bit lucky here. The numbers that I pull out are the coefficients in front of the chemicals I'm using here. I'm using NH3. Which has a 1 in front of it. So I put a 1 on that part of the fraction bar. And I'm also using this NH2Cl, which has a 1 in front of it. So I put a 1 up by it. So my mole-to-mole ratio is going to be 1 mole of this makes 1 mole of that. One of these makes 1 of these. If I had 2 of these, it would make 2 of these. Right? And that's going to be my conversion. Maybe do this. So if you like giving it a name, again, this is called the mole-to-mole ratio. Okay, we're moving right along. Our moles units, moles NH3, moles of NH3, cancel out. So I've now found an amount of NH2Cl, but that's not where I'm stopping. I don't care about the number of moles. I want to know how many liters of gas this is going to take, how much of the room I'm going to fill up with this. Okay, so Last step uses this little shortcut. At STP, we know that 1 mole of gas fills up 22.4 liters of volume. Well, what do I need to cancel out? Moles of a gas. What am I trying to get to? Liters of a gas. So that's what's going to be our last fraction bar. I have too many markers and nowhere to put them. H2Cl. H2Cl. Right? So at STP, 1 mole of gas. This still goes along with, as long as it's not moles over moles, we can be 1 with moles. Gives us 22.4 liters of gas. Okay? And the last unit that I don't want gets canceled out here, leaving me with liters of NH2Cl, the thing that I wanted. Okay? Now all I have to do is plug everything into the calculator. Set some of this stuff down. Okay. So just like with any fraction, we're going to be multiplying by the top and dividing by the bottom. You can do it multiplying all the way through the top first and then dividing by all the bottom. You can do the way I like to do it, where it's multiply, divide, multiply, divide, multiply, divide. As long as you punch everything in right, it's fine. So let's try this out. I'm going to move out of the way of the camera so you can see the whole thing. I keep blocking it. So 26 times 1 divided by 17.04 times 1 divided by 1 times 22.4 divided by 1 gives me 34.18-ish liters of gas, which is probably not good for the theoretical person that is doing this scenario here. All right, so we wind up with 34.18-ish liters of our toxic NH2Cl gas. Okay, so the stoichiometry is not much different. If you got the hang of the stoichiometry before, this is just one new thing you can plug in. The problems aren't really any longer yet. It's just kind of, a new trick you can throw in, something else we can solve for aside from grams and moles and particles. Now, if you didn't get stoichiometry before, hopefully this is where it's going to start making sense. Maybe giving it a break and then coming at it a second time will make it finally click. So hopefully that will happen for you. Okay, let's look at another example. Okay, if making the chloramine wasn't bad enough for us, or for this theoretical person that's doing this, that chloramine can wander around as a molecule in the gas phase and run into another molecule of ammonia that we kind of had from before, and those can react to make hydrazine, this N2H6. Okay, it is essentially what's used for some rocket fuels. It is also toxic. It is not good. So we just kind of made our situation worse. HCl is also an acid. It's a strong acid. It's hydrochloric acid. So that's also not good to have floating around in your air either. So it just kind of keeps getting worse. So we're going to continue on with this volume of gas to see how much hydrazine it could turn into. If all of this NH2Cl could react following this reaction equation, how much of this, volume-wise, will we make on the other side? So in this case, we are starting with 34.18 liters of NH2Cl gas. We are still freezing our butts off at STP, and we want to figure out how many liters of N2H6 gas we can make. Now, you may have noticed I've thrown in some G's here, right, in case it's been a while since we've seen these. These show us the phase of matter that our chemical is at. So we use G for gas, we use a little curly L for liquid, we use S for solid, and then we'll talk about another one, AQ, in the next unit, for aqueous stuff that's dissolved in water. Okay, so we've got all gases, we've got everything at STP, so we are free and clear to use that special little shortcut where 22.4 liters of gas is filled by just 1 mole of gas. All right, so we're going to convert this going from liters to moles of something else to that liters of something else. Okay, so this one I'm going to go a little bit faster. First step, I'm trying to get rid of liters. So liters has to go on bottom. Okay. Always next step has to be moles. All right. This conversion factor is moles and liters. At STP, 1 mole is 22.4 liters. 1 with moles, 22.4 liters. My liters cancel out. So I get moles over here. Okay? I don't want to stop at moles of NH2Cl. I want to know about hydrazine, N2H6. Okay? So I want to get rid of moles of NH2Cl. I'm getting all mixed up. All right? Moles of NH2Cl. All right? And then I am going towards, oops, let's change colors. Moles of N2H6. Okay, now, finally, I want to figure out how many liters of gas that's going to be. So, I can get out of moles by canceling it down here. And getting to liters up on top here. Okay? Now, this is still moles and liters together in a single conversion factor. So, it doesn't matter what kind of gas I'm using. 1 mole of gas at STP fills up 22.4 liters. So, it could be N2H6, it could be NH3, it could be H2, it could be CO2, it could be O2. Doesn't matter. Okay? If there's a difference in the mass of the molecule and how it takes up space, we take care of it when we're dealing with mass in a fraction bar like this over here. Okay? Once we have it in moles, we treat all particles the same because we're talking about them as particles. Okay? Whether the particle is this big or this big is not going to make that much of a difference. We can't even tell. It's negligible. Okay? So, let's fill in the rest of this. Whenever I have moles over moles, I look at my reaction equation. Again, we get lucky. I have 1 mole of NH2Cl that changes into 1 mole of N2H6. 1 mole of this can be used to produce 1 mole of this. So it's just 1 over 1. Okay? If this were a 2 and this were a 3, I would just put the 2 down there and a 3 up here. All right? We just look at whatever the reaction equation is. Final step. Again, doesn't matter that it's a different gas. 1 mole of this gas fills up 22.4 liters of this gas at STP. So all I have to do now is make sure all my units cancel. My moles cancels out there. My moles of N2H6 cancel. And I'm left with liters of N2H6. Now all I have to do is plug in my work and see what I get. Punch it in. 34.18 divided by 22.4 times 1 divided by 1 times 22.4 divided by 1, 34.18. That just seems weird. Did I do something wrong? Well, no. Since we're treating our gas particles the same, all right, we're not worried about them having a different mass. We're looking at how much space they take up. So it would make sense that this amount would feel the same as this amount, right, if we have the same number of moles of each. If all my moles of this make the same number of moles of this, then I should expect them to take up the same volume. Now, if I were to make twice as many moles of my new gas over here, then I should expect twice the volume. If it takes up, if it takes half the number of moles, I should end up with half the volume, and so on and so forth. But in this case, since I've just got a 1-to-1 ratio on my moles, I get the same volume of gas. So nothing went wrong. It's just how it goes. It's one of the kind of benefits of simplifying the gas at standard temperature and pressure. All right, let's do a couple more examples. The first a little bit easier than the second, so I've kind of already laid out the stoichiometry that we're going to hit. So in this first example, we're looking at burning propane, C3H8, in oxygen, O2, to make CO2 and H2O. Now, this is not a reaction that's just ones all around. One molecule of C3H8 can react with 5 molecules of O2 to make 3 molecules of CO2 and 4 molecules of H2O. So that means if I start with 1 mole of C3H8, it has to react with 5 moles of O2 to make 3 moles of CO2 and 4 moles of H2O if I want this reaction to work. I'm starting with grams of oxygen, and I want to figure out how many liters of CO2 I can make, and I'm still at STP to make the process a lot simpler. So we're following a similar kind of pattern to kind of our first example. We are getting rid of grams, we're converting to moles of the other gas, and then we're trying to solve for liters of CO2. So let's plug in what we can figure out. So since we are working with O2, and we've got a molar mass to put into this conversion factor, we need to add up the mass of 2 oxygens per 1 mole. So you look at the periodic table, you find oxygen, you add up the molar mass of 2 of them. Each oxygen should have a molar mass of about 16, so 2 of them would be 32 grams per 1 mole of O2. So we're one with moles. All right. Now, our mole-to-mole ratio is, again, the only time we cannot just assume we can be 1 with moles. All right. So in our reaction in this case, 5 moles of O2 can make 3 moles of CO2. That's that ratio we want to use in here. 5 moles of O2 makes 3 moles of CO2. It's kind of like our kind of currency conversion. How much of this can I get for that? Okay. Finally, our last step, we've got to get rid of moles of CO2 to make liters of CO2. Since we're at STP, 1 mole of gas, 1 with moles, should give us 22.4 liters of volume. So all that's left is to plug it in. Okay. 13 times 1 divided by 32 times 3 divided by 5 times 22.4 divided by 1. And I get about 5.46. liters of CO2 should be produced in this reaction as I burn up this propane, either from a gas grill or a Bunsen burner or something like that. Okay, I'll just circle my answer. Okay. Now, while we're on the topic of burning stuff in oxygen, this is the reaction that takes place when you are burning acetylene. So if you have like an oxyacetylene torch or something like that, this is typically the reaction that happens. And then your CO and H2 may go on to react to make CO2 and water. So this is kind of an incomplete combustion reaction that's going on first. Okay. Now, carbon monoxide is poisonous. That seems to be the topic of today, is just poisonous gases that can kill you. So carbon monoxide poisoning is pretty serious. You hear it a lot of times with people leaving their cars on in garages. I believe potatoes also release carbon monoxide, so I guess don't fill your house with potatoes and let them sit forever. So, okay, anyway. So we've got this acetylene torch. And we've gone on the internet and we've kind of run some numbers. And we figured out that we don't want to breathe in up to 735 grams of carbon monoxide in one good single breath. That kind of fits the poison tolerance for humans. Okay, so back in the envelope calculation says this is kind of our limit. So if everything were to go wrong, the room was not well ventilated, and we just somehow managed to get this much CO all in one breath before it can go and react into CO2, then we could be in trouble. Or maybe we're just environmentally conscious. Carbon monoxide is one of those greenhouse gases that's pretty nasty and is not helping our climate. So maybe we're trying to keep that down. We're trying to keep down our amount of C2H2 that we use. In either case, we are starting this time with how much of the product that we are expecting to make, kind of worst case scenario. And we want to figure out how much C2H2 I don't want to use kind of to get that amount. So I'm starting from a product and getting a reactant. That's fine. All right? We typically work from left to right on the stoichiometry diagram, but that doesn't mean we have to use a reactant and then a product. We can stick whatever chemicals we want where. We can go from a reactant to a reactant, a product to a product to a reactant, or a reactant to a product. Doesn't matter. As long as we are careful about what we convert with, what we put in these fraction bars. Okay? So we've got our acetylene torch. We light it up. All right? And so we want to see how much acetylene would need to be used to get 735 grams of carbon monoxide, CO. So let's set this up. I'm getting rid of grams of CO first. That takes me to moles of CO. I'm one with moles. The molar mass of carbon is 12.01. Oxygen is 16. So this molar mass is 28.01 grams per mole, right? Should be. $16, $12. Yeah, okay, yeah. I doubt myself there. Okay, so grams is gone. Next step is to get rid of moles of CO. All right. I'm trying to get to moles of C2H2. Okay. My reaction tells me that 2 of these are produced for every one of these that I use. So I just match up the coefficients with the chemicals. The 2 out in front of here goes with the moles of CO. The 1 out in front of here goes with the moles of C2H2. All right. Finally, I do what we have been doing. We're trying to get to liters. So as long as we're at STP, 1 mole should make 22.4 liters. But we're not at STP this time. I have a pressure of 0.98 atmospheres. Standard pressure would be 1 atmosphere. And we're also not at standard temperature. That would be 273.15 Kelvin. We're a little too high for that. So this isn't going to work. I can't do this last step. I'm stuck at moles. So does that mean I can't figure out the volume of this gas? No. It just means it's going to take a little bit longer because we were just working on something that put together the pressure and the volume and the temperature and the amount in moles of a gas. Okay? So if I'm trying to find volume and I'm missing that piece, but I have the pressure and the temperature, and I can use this to find the number of moles of C2H2, I can pick a gas constant to go with my pressure in atmospheres, and then I'm just solving this out in the ideal gas law. So let's do that. Let's do this one last thing. All right, so we can't figure out the volume of a gas just with stoichiometry alone if we are not at standard temperature and pressure, okay? Which in this case we're not. We've got our pressure at 0.98 atmospheres. We've got our temperature at 294 Kelvin. But this is the perfect scenario to use the ideal gas law. Okay? So, we've got our P, we've got our T. Those were given to us. We can pick an R constant to fit our pressure unit. So we're using the 0.0821 atmospheres liters per mole Kelvin. We're looking for volume. So the last thing that we need is our N, our number of moles. That's what we can get from the stoichiometry we've been working on. So if I take my 735 grams times 1 divided by 28.01 times 1 divided by 2, that's going to give me a number of moles of this gas, of C2H2, which is the N I'm looking for. So let's calculate it. 735 times 1 divided by 28 gives me about 13.12. That is quite a bit of acetylene we have to use. All right, so 13.12 moles of C2H2. That is my N in my PV equals nRT. Okay? Now I just have to plug everything in and solve for V. All right, so we got everything plugged in here. We just have to solve for the volume. So I'm going to kind of do my math shortcut where instead of having to divide everything on both sides or multiply everything on both sides, I'm just going to kind of move things over. So if something's being multiplied and I need to get rid of it, I divide it over to the other side. It's like we do the opposite thing to get it over to the other side of the equal sign. Okay? First, I'm going to condense all of this stuff on the right just because I like working with smaller numbers or less stuff kind of jumbled up over here. So let's put these together. .12 times 0.0821 times 294 gets us 316.68-ish. Right? My units, well, moles on top and bottom, cancel. Kelvin on top and bottom, cancel. What I've got left is atmospheres and liters. And that's still equal to my 0.98 times my V. All right, so to solve for V, I just need to get rid of this 0.98 atmospheres. You can divide both sides by this 0.98, or you can do the shortcut I like to do, where I'm going to move it under to divide it. Okay, so I'm dividing it over here, and by tossing it over here, it's no longer there. So I'm going to get rid of it. All right, so that should just leave my V on the left side here. So V, my volume, should be equal to this 316.68 atmospheres liters divided by my 0.98 atmospheres. My atmospheres unit should cancel. So I should just be left with liters, which is good for finding a volume. Take this divided by 0.98. And I get 323 point about 15-ish liters. All right. So sometimes we need to use a combination of gas stoichiometry and the ideal gas law. There's a reason why we go through all these different methods. It's because each tool kind of has its own time in the sun when it's really useful. Right? This is especially good for when we're working in a lab, like we're going to do later on this week here, or depending on when you watch the video, whatever. But later on, we're going to use this method because we don't usually have our lab conditions at standard temperature and pressure. That's way too cold. It's kind of like torture. So at a higher temperature, we can't use the 1 mole equals 22.4 liters of volume shortcut. Instead, we go to the ideal gas law.